Let's see here. Okay, our session's being recorded. We're going to talk about initial value problems, section 1.2. All right, and this is the first example. So let me give you a moment to copy this example down, and then we'll discuss its solution, okay? Again, I believe I tend to like to, if I can, I like to do examples to help reinforce definitions and things. So, all right, let me give you a moment to copy that down. Are there any questions so far? All right. Matthew's good, very good. All right. All right, I'll be right back. Okay, so here we are. All right, so in this, so we learned last time, we actually last time had a differential equation and showed that a solution, that we proved that a function was a solution to the differential equation, and the function had a parameter in it, a constant c. So in this problem, okay, we're being told that y equals 1 over x squared plus c is a one parameter family solutions to the differential equation y prime plus 2xy squared equals 0. And we're being asked to, well, I want to be, so we could show this, right? We could show this. We know how to show this. You had these kind of problems in your homework. But what we want to do now is add a condition to the differential equation. And when we do that, we get what's called an IVP. IVP, okay, IVP stands for an initial value problem. That's an abbreviation for initial value problem. So you see, we have here a family of solutions. Y equals 1 over x squared plus c is a family of solutions to the differential equation. And it's a family because that c value here could be any number in this case. C could be any number. And, you know, if you were to graph y equals 1 over x squared plus 4, y equals 1 over x squared plus 3, y equals 1 over x squared plus or minus 7, you know, you would have a family of solutions. But if we add an initial condition such that when x equals -2, y equals a half, then we're going to get under normal circumstances, we're going to get a unique solution. We're going to get one solution. In other words, having this initial condition will then allow us to, we'll get that information allows us to solve for that constant c. But of course, it's specific to the initial condition. Different initial conditions will give us different values of c. So what we want to do is solve this initial value problem, and then we want to give the largest interval I over which the solution's defined. Okay. So I'd like to move to the solution. Is everybody good so far? Let's see. All right. And Matthew says the first step is to take the derivative. No, we're not. We're like here. We are. They're like you're not in the example being asked to show that this is a solution to the differential equation. They're telling you it is, and you're taking it on faith. So we're going to accept that is a solution, a general solution to the differential equation. You know, y equals 1 over x squared plus c is a general solution to this differential equation. We're going to take that on faith. But what would the solution be? What would the solution be to the differential equation when we add this initial condition? What we're saying is that the solution has to pass through the coordinates -2.5 in the xy plane. That's what we're saying. So let's go ahead here and work the solution out. So we're given the solution is y equals 1 over x squared plus c. And that means then, you know, we understand that y is a function of x. So y equals 1 over x squared plus c is equivalent to saying that y of x equals 1 over x squared plus c. Well, when x equals -2, the value of our solution at that x value is a half. Okay. So what we do is we plug -2 in for x. That's what we do. And we'll get 1/2 equals 1 over 4 plus c. And so c will equal -2. And so now we have a value. Now we have a value for our for that constant. And so we can say the solution to this initial value problem, again, the initial value problem has a differential equation and an initial condition on the solution. The solution to our initial value problem is y equals 1 over x squared minus 2. Okay, are there any questions so far?
Can you explain that again, please?
Sure, sure. So we have a general solution to the differential equation, y equals 1 over x squared plus c. And now, by specifying an initial condition, we can solve for the parameter c. We can solve for that. If when x equals -2, y equals a half, if that's our initial condition, that means then that the solution, the solution has to satisfy this initial condition. And that means then that c would equal -2. We're good up to here? Yeah, that's right, Wajija. We take the condition and plug it into the solution. That's right. That's exactly right. And so the solution to our initial value problem, okay, initial value problem is the differential equation accompanied by an initial condition. The solution then is y equals 1 over x squared minus 2. Christopher's good. Okay, very good.
So
Very good.
essentially, this whole process is to just solve for c and plug into the given problem.
That's correct.
Okay.
That's right. That's right. That's right, Christopher. All right. All right. Well, now in the problem, we want to find the largest interval over which the solution is defined. Okay. So to answer that question, it helps to draw a little picture. So on the next page, I drew in my XY plane, well, remember, y is equal to 1 over x squared minus 2. But the denominator can be factored as x minus root 2 and x plus root 2. So what values of x would, y equals 1 over x squared minus 2, what values of x would not be allowed? What values of x, and you can chat it in the window, based on the denominator here, what values of x would not be allowed? What can x not be? In other words, what's the domain of, if you just think of 1 over x squared minus 2, just think of that function, what x values are excluded from the domain?
Negative root 2 and root 2. That's
exactly right. That's exactly right. Justin, Christopher, that's right. That's right. So, and Wajija, I'll answer your question. I see you have a question. So what I've done is in the XY plane, I've drawn asymptotes at negative root 2 and positive root 2. Okay, but the largest interval over which the solution is defined is negative infinity to negative root 2. Now, what's that about? What's that about? So the domain of the function 1 over x squared minus 2 is all real numbers except negative root 2 and positive root 2. However, keep in mind, we are looking at the solution of an initial value problem. So yes, the function is 1 over x squared minus 2, but we're demanding that solution pass through the coordinate negative 2, 1/2. The solution has to satisfy that initial condition. When x equals negative 2, y equals 1/2. And so when we draw the solution is going to be contained, well, the xy plane, you notice, is broken up into 3 segments. Here's a segment here, okay, when x is greater than root 2. Here's another segment, or a partition, when x is between negative root 2 and root 2. And then here's another partition, when x is less than negative root 2. So the solution, since it has to pass through the point negative 2, 1/2, this is what the solution looks like. And so the largest interval over which the solution is defined is right here. It's this one. It's that left partition, and that's then from negative 1/2 to negative root 2. In other words, the solution does not exist here, and it does not exist there. It only exists as you seen it drawn here in the picture, right here. Wajia, are you comfortable with that?
Yes.
Excellent, excellent. All right. Are there any questions on this?
I have a quick question. What
All
is
right,
the
Justin.
significance of asking for the largest interval? Is that just what the question was, or is there some sort of, like, are we going to be dealing with largest interval?
You're going to have questions like that. Well, you know, you could say that. Well, I mean, would the solution exist if I were to say, restrict the solution to be, let me see here, negative root 2 is like it's negative 1.4, right? So if I were to restrict the solution, let me phrase it the way I want to phrase it here. Let me ask you this: does the solution exist over the interval from negative 3 to negative 1.5? Does the solution exist on that interval?
Yeah.
It does. But is that the biggest interval over which the solution exists?
No.
No. The biggest solution is the entire this entire, you know, partition, which goes from negative infinity to negative root 2. An open interval, of course.
Okay. Thank you.
All right. All right.
I think he was asking, like, so is this largest interval, are we going to have anything specifically to do with the fact that we found the largest interval rather than just some interval?
Well, we're really interested in the largest interval over which the solution's defined. That's really, and I know it's kind of Why not just say what's the interval over which the solution's defined? And then you say negative infinity to negative root 2. That would be, I mean, really, that's what they're asking. But they get a little bit technical sometimes. And really, when they say what's the largest interval over which the solution's defined, essentially think of that as like, what's the entire interval over which the solution's defined? Think of it like that. All right, Matthew's good with that. All right. If there are there any other good questions before we move on? All right, all right. Well, let's move to a next example. Okay, this is a big example here, this next one, but it's going to hit upon a lot of things. So I like to have examples. I think about when you're doing your homework, you know, questions that'll come up in homework, and I try to pick up problems that, you know, will be most helpful. So let me give you a moment to copy this example down. Okay, all right. So here, there are three parts to this question. Now, the first part says we want to show that 3x squared minus y squared equals c is a one-parameter family solutions of this differential equation. Now, the way they write the differential equation is y times dy dx equals 3 times x. But of course, this is equivalent to saying dy dx equals 3x over y. So I don't want you to get confused when, like in the homework, maybe they restate things in a little bit different way. I mean, this is the differential equation they're talking about. They just wrote it this way. All right, so we're going to show that 3x squared minus y squared equals c. And we could solve that in terms of y, but they write it this way. Show that that's a one-parameter family of solutions to the differential equation. And then on part B, we want to solve an initial value problem. Okay, where in addition to the differential equation, we're given that when x equals 2, y equals -4. Okay, and then we'll get to part C, but let's go ahead and proceed forward here. We're good. Everybody has the example copied okay?
It's nonlinear.
Antonio, you're good? All right, good. All right, Andrea's good. Andrej, excellent. Okay, how many remember implicit differentiation from calculus 1? Implicit differentiation. That's back. Okay, well, I'm sure you've all seen it. All right, well, let's go to the solution here. Here's how you're going to do this. Okay, it's difficult to write. If we were to write this solution as, we could write it. We could write it as let me see here. What if we were to solve that? If we were to solve that for y, we'd have y equals plus or minus the square root of 3x squared minus c. Okay, and so to show that this is a solution, we'd have to do two proofs because we got a plus and a minus. So it's easier just to use implicit differentiation. So what I do is I take, with implicit differentiation, I'm going to take, and actually I guess we start it here really. We take the derivative of the left side of the equation with respect to x and the right side of the equation with respect to x. But we keep in mind that y is some function of x. Okay? I mean, if you give me an x value, I'll give you a y value. Okay? I mean, given some x, we can solve for y. So we differentiate both sides of the equation. The derivative of a difference is the difference of the derivatives. The difference of two functions is the difference of the derivative of each function. The derivative of 3x squared is 3 times 2x. The derivative of y squared is 2 times y times dy dx. Now, what special rule did we use when we say the derivative of y squared with respect to x is 2y times dy dx? What special rule did you use from calculus 1? What rule are we using there? Good, Hyung and Michael. The chain rule. Using the chain rule. All right, so then the derivative of a constant is 0, And so now we get 6x minus 2y dy dx equals 0. Are there any questions up to this part here? All right. Well, so of course, I want to get that y times dy dx equals 3x. So hopefully I can manipulate this result so that I get y times dy dx equals 3x. All right, well, let me then add the 2y dy dx over to the right side. And then I will divide both sides by 2. And we got it. We got it. Y dy dx, okay, y dy dx does equal 3 times x. It does. So it checks out. That is a family of solutions. 3x squared minus y squared equals a constant is a family of solutions to the differential equation. Okay, are there any questions so far? All right.
What does it mean?
Yes,
What does it mean when they
Wajid.
say- What does it mean when they say one parameter?
Well, it's a one parameter family because you just have one unknown constant here. You can have problems where you have problems, and you'll see this in your homework, where you're given a general solution like, y equals c1 times x plus c2 times x squared. That would be a 2-parameter family of solutions. Something like that would be a 2-parameter family. And in order to solve a 2-parameter family of solutions, something like this, you would need to have 2 initial conditions. For a 1-parameter family of solutions, to solve for the constant, you only need 1 initial condition. But if you have 2 parameters, like here, you need 2 initial conditions. All right, so in this problem now, in part B, we want to solve the initial value problem. So y of 2 equals -4. All right, so we're going to put in our initial value of 2, -4 into the family of solutions so that we can solve for the constant. How many remember doing initial value problems in Calculus 2?
I remember them.
Yeah, you saw them. You saw them. Well, and you're seeing them again. And so in this case, C turns out equals -4. And so the implicit solution to the initial value problem being dy dx equals 3x over y, with initial condition y of 2 equals -4, this is your implicit solution. But of course, you're used to seeing explicit solutions. Okay, you're used to like in Calculus 2, you would solve a differential equation using like separation of variables Okay, and you would get y equals a function. Well, we can do that. I mean, I can rewrite this implicit solution as an explicit solution. Okay, an explicit solution would be where you're letting where y equals something, equals a function. And so all I need to do is solve for y. Okay, let me give you a moment to copy down to here, and then we'll talk about like why I chose negative, a negative in front of the square root.
Sir, what does it say in the parentheses in the initial value area towards like the top of the paper?
Towards the top. Oh, this says a family of solutions to DE. DE is differential equations.
The one under that, actually.
Oh, that just says initial value. The initial value is 2, -4. In other words, when we say that y of 2 equals -4, that's the same thing as saying that the solution to the differential equation has to pass through the point 2, -4.
Okay, gotcha. I thought it was 2 sub 1, so thank you.
Oh, no, that's a comma.
Yeah, thank
I'm
you.
glad you asked. That's a comma. Yeah, always ask. Always ask. Okay, all right. So now down here, okay, like when you have y squared equals 3x squared plus 4. Let me just clear this for a moment. When you have y squared equals 3x squared plus 4, if you solve for y, right, you're going to get y equals plus or minus the square root of 3x squared plus 4. But under normal circumstances, can we have two solutions to a differential equation? Do we want two solutions to a differential equation? When we have I should be careful. When we have an initial value, we have a differential equation with an initial value. Do we really, I mean, do we want two solutions, or would we like just one solution? What's better? Definitely one. It's you know, it's like confusing to have more than one solution to an initial value problem. And thankfully, under normal circumstances, when you solve an initial value problem, okay, there's a theorem. It's called an existence of solution theorem, 1.2.1 in section 1.2. Under normal circumstances, you will get a unique solution. But the question is, all right, are we going to choose the plus or the minus? Well, remember, y of 2 is equal to -4. Okay, so when x equals 2, y is negative. And so, so you have to choose the negative here. You have to choose the negative. I mean, think about it. Put x equals 2. Put x equals 2 in your solution. You're going to get the square root of 3 times 2 squared plus 4, which is the square root of 16, which is 4. But when x equals 2, y is negative. And so that's why you pick the negative. Okay, does that make reasonable sense? All right, Ann's good. Kathia's good. All right, let me know if you have any questions. Christopher's good. All right. All right. So if you had another condition, let me ask you this. What if y of 2, let me be careful here, hold on. What if y of 2 were equal to positive 4? What if that were instead your initial condition, that y of 2 was equal to positive 4? Got to be a little bit careful here. One moment, class. I want to make sure you would have to choose the positive. That's right. I'm just going to keep it simple. Okay. In other words, you use the initial condition to help you. But that being said, let's move on. Let's move on. All right. Now the last part of the question says, are there any explicit solutions of the differential equation that pass through the origin? Well, if you're saying you want a solution to pass through the origin, okay, then what's the initial condition then that corresponds to that? If you want your solution to pass through the origin, right, y of 0 would equal 0. Okay. Now here's the you know, here's the thing. Here's the thing. dy dx equals 3x over y. Okay. So could there be an issue at the origin? Like the solution that this solution here, 3x squared minus y squared equals c. We have to be careful. We have to be careful because 0, y in the denominator, y equals 0 is undefined. Okay, so, but yet there are solutions that are going to work here, and let me show you why. Well, let me show you here. Okay, so this here, there's a theorem in your textbook that talks about the existence of a solution. Okay, it talks about the existence of a solution to a differential equation. And what we care about is the existence of a unique solution. Well, clearly, the differential equation, the right-hand side, like if you write the differential equation as dy dx equals a function of x and y, clearly the function of x and y, which is 3x over y, clearly that function is not continuous at the origin. It's not continuous at the origin because you have a y in the denominator, so you can't have 0 in the denominator. Okay, so the function is not continuous at the origin. But there's also another condition too that comes up in this existence theorem, theorem 1.2.1. It turns out that if you take what's called the partial derivative of your function with respect to y, and if you take Math 280, multivariable calculus, you'll have seen partial derivatives, but you're not going to have to know how to take a bunch of partial derivatives in this course. But this is the only theorem that I'm aware of that refers to a partial derivative, at least in chapter 1. When you take a partial derivative of a function, it's like you're taking the derivative of this function, 3x over y, with respect to y, but you hold the x constant. Okay, you can only differentiate with respect to one variable. Okay, so you can only differentiate with respect to one variable. So if you're gonna differentiate with respect to y, you hold the x constant. So the 3x on top is treated like a constant, and the derivative of 1 over y is negative 1 over y squared. So the partial derivative of f with respect to y equals negative 3x over y squared. And that partial derivative is not continuous at the origin. This means that this, I should really not call it a DE, it's an IVP, an initial value problem. This initial value problem may have multiple solutions at the origin. In other words, things kind of go crazy. We love having a unique solution to our initial value problem. But since the conditions of our differential equation do not satisfy the theorem 1.2.1, we can end up having multiple solutions to the differential equation going through the same point. And I'll show you what those solutions are. I mean, this is not something we want. It's not something we desire, but we have to be aware of it, you know, for our mathematics. Okay, so, well, I'm going to show you, Zachary. That is correct, Zachary. There could be, so let me go to the next page, and this will be a little more clear to you. This will be a little more clear. But let me make sure everybody's had a chance to copy this down. All right. Thank you, Matthew. Does anybody else need a little more time? Right. Well, the reason why the partial derivative is not continuous at the origin is because the y equals 0 makes that partial derivative in the denominator there, makes that partial derivative like does not exist. Now, I want to make a comment here. When you look at the differential equation as it's written here, y times dy dx equals 3x, you're not, I mean, you know, you're not dividing by y. So there could be solutions to that differential equation. Where the solutions pass through the origin, because you're not dividing this differential equation as it's written. I mean, writing dy dx as 3x over y is a next step. But if we just focus on this differential equation in its pure form, we don't have to worry about that. And remember, the family of solutions satisfies the differential equation in its pure form. Okay, this here, when I divide by y, that's just taking it a step further. But we don't have to do that. I mean, we don't have to do that. And here, what I'm going to do is I'm going to solve the initial value problem, this one here, for the initial value 0, 0. So I work the problem out. Just like before. I'm going to try to solve for that parameter c, and I solve for the parameter c, and I get c equals 0. Okay, I get c equals 0. And so the solution to the initial value problem, and I really need to be careful here. This is not, technically this is not how I want to write it. I want to write it like this. Let me fix that. I want to write it as, hold on here. I want to write it as y times dy dx equals 3x without that y in the denominator. Okay. Yeah, this is the next page. This is right. We've only gone forward one page. So this is the initial value problem that we're solving. Okay, this is the initial value problem that we're solving here. Okay. And technically also, let me even be more clear here. On the previous page, when I mentioned the initial value problem, right here, we should maybe write that as, we can write that as y times dy dx equals 3x. Although it is correct in this case, the way I wrote it as well. But we can do that. In other words, we can do that. Okay, so going back here then, okay, remember what we're doing. We are trying to solve, go back here. We are trying to solve this initial value problem. Well, that differential equation, given that y of 0 equals 0. And so here's the family of solutions that satisfies that differential equation. So we're going to put in 0, 0 into the family of solutions, and we'll get c equals 0. And so therefore, the solution to this initial value problem can be shown to be y equals plus or minus √3 times x. Let me give you a moment to catch up here. Let me give you a moment to catch up. You have a problem like this in your homework, and I think this is going to, I think this will help you. A lot. I can bring that up in the ebook, Michael. I can bring it. Michael's asking about stating formally the existence and uniqueness theorems. It's in the ebook, and I can bring it up. That's not a problem. Not a problem at all. Not a problem at all. So we end up here. We end up with we solve for y to get the explicit solution, and look what happens. We get two solutions, and both the solutions pass through the origin. Both of them. The plus and the minus work here. Y equals, in other words, y equals plus root 3 times x, and y equals negative root 3 times x. Both work. They both satisfy the initial condition. So when you have a situation where you write the differential equation as dy dx equals a function of x and y, and that function of x and y is undefined at your initial condition, or the partial derivative of that function of x and y with respect to y is undefined at your initial condition, you can get multiple solutions. And they also have an example 4 in the book, in the ebook, shows that as well in section 1.2. Now, Michael asked if I could bring up hold on here, if I can bring up just the formal theorem, and I'll do that. I'll end the lesson that way. One moment. I didn't bring up the theorem right away because I think when you see the theorem, it's quite technical, but at least now you've seen an example of the application of the theorem. Hold on just one moment. Let me get it here. One moment. Hold on, class. Just let me find it here. It's here. It's here. Okay, one moment. Let me go back in here. So Wajija, the square root of 3x squared, the square root of 3x squared is the same as the square root of 3 times the square root of x squared. And the square root of x squared is the square is just the x. Okay? Does that make sense? All right, good. Are there any other good questions? I'll get to the theorem here quickly because I know it is after 6:15. May I? Everybody has this copied, okay? All right, wonderful. Let me get to that theorem. Hold on here. Okay, now we'll just let the phone ring here for a moment. Hold on. Yeah, don't ignore the phone. This is the theorem right here. And the theorem, I don't want you to get bogged down, and it's very technical, quite technical how it's written. Don't get bogged down in the technical details. I've shown an example of an application of the theorem, and that will be satisfactory for your homework. Okay?
Professor,
Okay. Yes. Mike.
speaking of homework, I'm on WebAssign now, and it says no current assignments.
Okay, hang on. Let me stop the recording. There's a reason for that.
Oh,
Hold on. Well, I'll keep the reason I took them off is I don't want anybody working on the assignments during the lecture. But
okay.
now I'm going to activate them. Isn't that something, Christopher? How about that? Is Dr.